Finally, we arrive at Galois theory. Galois theory is one of the jewels of mathematics. It allows us to solve polynomial equations by exploiting symmetries coming from group theory and linear algebra. One of the big results from classical Galois theory: can't solve a general quintic polynomial equation using radicals. So what's that mean? Well, we have the quadratic, cubic, and quartic formulas, but there's no quintic formula. So this is a case of where mathematics tells us that we can't do something. Now, modern version of Galois theory is what we call the Langlands program, and its recent successes include proof of the Fermat conjecture, that went unsolved for over 300 years, and a proof of the fundamental lemma. There's much work to be done in the Langlands program, so this is a very active field of study. Now, for us, we're only interested in classical Galois theory, so we'll start with groups, and in this part, we consider only Galois groups. We'll look at other automorphism groups later on. For here, we just want to get a feel for Galois groups, what they do, and to review basic group concepts. Now, to begin, pick a field f. We'll have g a polynomial over f. I'll let n be the degree of g. We can assume it's bigger than 1. And we'll choose k a splitting field of g over f. So that'll be some smallest extension of f containing all the roots of g. Now, we have a lot of choices here, but they'll all be isomorphic to one another. Simplest way to express the splitting field, we take f and we just adjoin all the roots. If I want control over the size of the splitting field, we note the degree of k over f is always less than or equal to n factorial. Now, definition, we have k a splitting field of g over f. We'll define the Galois group of k over f to be the group of all automorphisms of k that fix f pointwise. Then we denote this with gal and then k slash f. First, let's check that this set is in fact a group. Now, the group operation is going to be composition. The elements are going to be automorphisms of k that fix f. So to be an automorphism of k, what do we need? Well, it's going to be a field isomorphism, k back to itself. So that means ring isomorphism. So for ring homomorphism, we have these 4 properties. And then we want 1-to-1 and onto. Now, to see that we have a group, we want to show 4 properties. First, closed under composition. So if I take 2 automorphisms, in general, compose them, we get another automorphism. We also want to check that if the automorphisms fix f pointwise, so does the composition. And that's a straightforward check. Next, the identity is just the identity automorphism, and we note that that fixes f pointwise also. Associativity just follows from composition of functions. Then finally, for inverse, well, these are automorphisms, so natural definition of inverse using set theory. And then we note you can run through all the properties to verify that this inverse is also an automorphism. We also have to check that the inverse fixes f pointwise, and that just follows from our definition here. Now we note there's nothing special about using a splitting field here, so this will work for any automorphism group of an extension k of f that fixes f pointwise. Now, we have a group. What kind of group can it be? The key idea we've seen before. So proposition, alpha is a root of g, phi is an automorphism of k fixing f, then 5 alpha is also a root of g. To see this, we apply g to 5 alpha. So I'll write that out. Because phi fixes f pointwise, pull phi to the outside. What's on the inside is going to go to 0 because alpha is a root of g, so 0 comes out. And that says that 5 alpha is also a root of g. And that's what we wanted to show. Now this says phi is going to move the roots of g among themselves, but even better, because phi is an automorphism, it does so in a 1-to-1 onto manner. So phi is going to permute the roots of g. Now for the group theory terminology, we say that we have a group action of the Galois group on the set of roots of g. Let's recall what a group action is. We have a group and a set. The elements of the group send elements of the set to other elements of the set, subject to the following 2 conditions. First, if we apply group elements to a set element in stages, it's the same as if we took the product of the group elements and then applied it to the set element. Also, the identity element of the group behaves as the identity mapping on the set. Now, that means we have a group action on a finite set, but even better, this action is faithful. So if I have a group element that acts as the identity on the set, it must be the identity element of the group. To see this, I can write K as f adjoin the roots of G. By definition, phi fixes f pointwise. So if it fixes the roots of G pointwise, everything's fixed pointwise, and phi must be the identity automorphism on K. To summarize, we have a theorem. There exists a one-to-one group homomorphism from the Galois group into the symmetric group on n letters. Now, that just means, we have the Galois group is finite with less than or equal to n factorial elements, where n is the degree of G. Now, here what's happening, the group action just says we have a homomorphism called pi from the Galois group to the group of bijections from S to itself. Now, this group is isomorphic to Sn, symmetric group on n letters. Because the action is faithful, that means the kernel of this homomorphism is the identity. So this map is going to be one-to-one. Now, for examples, familiar example, we have g equal to x cubed minus 2 over the rationals. The roots of the complex numbers, I have cube root of 2, omega cube root of 2, omega squared cube root of 2, where omega is e to the 2 pi I divided by 3. For the splitting field, k is equal to the rationals adjoin cube root of 2 and omega. So this contains all of these roots. And the Galois group is going to be isomorphic to S3. So this group has 6 elements. That's as large as possible, which would be 3 factorial. Now, for the Galois group, this is generated by 2 automorphisms. We have phi1 that sends cube root of 2 to omega cube root of 2, omega to itself, and complex conjugation. So this is an element of order 3, this is an element of order 2. We note these elements do not commute, so we have a non-abelian group, so it must be an S3. Now, feature of the group action here, the group action is going to be transitive. So there's a single orbit. So that means if we pick any of these roots, apply all elements of our group, we get back all of the roots. So that's a straightforward check. Another familiar example, fix a positive integer n. We let g be equal to x to the n minus 1 over the rationals. So here the roots are going to be the n distinct nth roots of unity in the complex numbers. So here we have omega equal to e to the 2 pi I divided by n. And then the roots are 1 omega, omega squared, up through omega to the n minus 1. For the splitting field, k is equal to the rationals adjoin omega. So the degree of k over f is going to be equal to phi of n. So this is the Euler-Totient function on n. For the Galois group of k over f, these are going to be the automorphisms phi sub k. So phi sub k is going to send omega to the kth power. To have an automorphism, the restrictions we put on k, well, we'll just pick k between 1 and n, inclusive. And I want k and n relatively prime. So we've seen this before. Now that means the Galois group is isomorphic to the group of units in Z mod n under multiplication. Note, our group has 5n elements, again, the Euler-Totient function, which is less than or equal to n factorial, in fact, strictly less than. How about the orbits under the group action? We'll fix an nth root of unity, say omega to the k, then we'll raise it to jth powers where j and n are relatively prime. That'll give a partition of the nth roots of unity as a disjoint union of the primitive dth roots of unity where d is a divisor of n. Now, for a concrete example, let's let n be equal to 10, so I have omega to the 10 equals 1. X to the 10 minus 1 has 4 factors. So these are going to be cyclotomic polynomials associated to the divisors of 10. So 1, 2, 5, and 10. Now for the Galois group, okay, we have Z mod 10 star, the group of multiplicative units in Z mod 10. These are 1, 3, 7, and 9. So we're going to take our nth roots of unity and raise them to powers 1, 3, 7, or 9. Now when we do that, we expect to get a partition into primitive dth roots of unity where d is a divisor of 10. So what comes out? Well, if we have 1, okay, that's going to be in its own orbit. Minus 1 is in its own orbit. If I take omega squared, okay, we're just going to take the exponent 2, multiply by these numbers. We have the primitive fifth roots of unity. If we take omega, okay, its exponent's a 1, we multiply by these numbers, we just get back the primitive 10th roots of unity. Now, an important thing to notice, okay, these orbits are going to correspond to the irreducible factors in our polynomial. We'll explain that in a little bit. For the picture, okay, what do we have here? Well, I'll draw in my 10th roots of unity. We'll have two pentagons. Okay, we'll take off the 1 and minus 1 since they're in their own orbit. Then the vertices that are left connected are going to be the orbits. So as so. So we have the even powers and the odd powers that are not 1 or minus 1. For an example with a finite field, okay, so there's a lot we still need to fill in here, but we can still talk about it. We'll let our base field F be the finite field with Q elements, where Q is equal to P to the M, where P is a prime. Polynomial, for G, we use x to the Q to the kth power minus x, where K is bigger than 1. The splitting field is going to be, okay, we have finite field with Q to the K elements. Then the degree of K over F is equal to K. Now, this in fact is a splitting field. Okay, you'll note every element in this field satisfies the polynomial x q to the k minus x, and it has as a subfield f sub q. For the Galois group, k over f, okay, this is going to be generated by a single element, so I'll call it pi sub q, which is just raising elements to the qth power. So this is going to be a cyclic group with k elements. Now recall, okay, we need to show this is an automorphism. Okay, we've noted this a few times. The key step here is noting that if I take pi sub q on alpha plus beta, that's pi sub q alpha plus pi sub q beta. And that follows from the binomial theorem since we have, okay, a power over prime. So over z mod p, the middle terms when we expand are going to drop out. The other thing to note, okay, so pi sub q is going to have order k, and pi sub q is going to fix f sub q pointwise. And that's just from noting that if we're in a finite field, okay, the units are going to form a cyclic group, okay, of order q minus 1 in this case. Here's a familiar example. What happens when we have an irreducible with multiple roots? Okay, that is what happens when the extension is not separable over f. I'll let f be equal to, okay, the rational functions in t over z mod p with p a prime. G is equal to x to the p plus t. If I pick splitting field k equal to f adjoin pth root of t, then g factors completely as x plus the pth root of t raised to the pth power by the binomial theorem. Now, in this case, we have a single root with multiplicity p. So the Galois group is trivial. Okay, it consists only of the identity automorphism. We note the Galois group still acts transitively on the root set if we ignore multiplicities. Now, that holds in general. So theorem, if G is irreducible over F, then the Galois group acts transitively on the root set of G. Otherwise, okay, if G is reducible, then the irreducible factors of G correspond to the orbits of the group action on the roots. Now, it's enough just to suppose G is irreducible over F. Okay, we could just be picking out a factor of G. Now, I want to show the action's transitive. So if I pick any two distinct roots of G, I want to construct an automorphism that carries one to the other. Now, the first step, we review the evaluation homomorphism from ring theory. So this lets us construct fields abstractly using maximal ideals. Now, we'll fix a root alpha of irreducible G, and then the evaluation map is just going to send the polynomial ring for F to F adjoint alpha. So we just take each polynomial and evaluate at alpha. This is a ring homomorphism. The kernel is just the ideal generated by G. And because G is irreducible, we have a maximal ideal. So if we form the quotient ring, we get a field. And this field, by our map here, is isomorphic to F adjoint alpha. Now, if we have distinct roots alpha 1 and alpha 2, we combine the evaluation maps to get an isomorphism carrying F adjoint alpha 1 to F adjoint alpha 2, sending alpha 1 to alpha 2. What about the splitting field K? K is a splitting field for G over F, so it's also a splitting field for G over F adjoint alpha 1 and F adjoint alpha 2. Our situation, we have an isomorphism of fields, and we have a polynomial over both fields. So if we chose splitting fields for that polynomial over each base, the splitting fields would have to be isomorphic to one another. Now, here we've chosen K as a splitting field in each case, so that just means there's an automorphism of K that extends this isomorphism. That is, we have an automorphism of K that sends alpha 1 to alpha 2, and that's what we were trying to show. Now, let's take a closer look at the case where we have multiple roots. So we'll assume that G is irreducible over F, and G has multiple roots. We've seen before, in this case, we must have characteristic of F is equal to P of prime, and that G can be written as a function of x to the P. So if I write G of x as h sub 1 x to the P, we check and see if h1 has multiple roots, and if so, we will repeat the process. So eventually I can write G of x as h x to the q, where h has no multiple roots, and q is a power of a prime. This lets us factor G in two ways. For the first factorization, okay, our extension is going to be the splitting field of h over f. In that case, okay, we could factor G into distinct linear factors as a function of x to the q. Okay, so all we've done here is factor h. Now, we know these roots are distinct, the betas. So for my next step, we're going to use the binomial theorem to pull the q out. And then we're working in the splitting field for G over f. So we'll call the qth root of each beta alpha. The alphas are all distinct. And we have our complete factorization of G. So here we've used two extensions to get to the splitting field of G. The first one is a separable extension, and the second one we call purely inseparable. Now we know, okay, the Galois group, well, the Galois group is going to act on the alphas by acting on the betas. So essentially, all the Galois group is doing is acting on this separable extension. For a concrete example, okay, I'll choose P not equal to 2. We're working over the rational functions in T over Z mod P. And I'll let G be equal to x to the 2p minus T. Now, for the first factorization, okay, we have this as so. So we have two irreducible factors here in terms of x to the p. Then when we pull the p to the outside, we have the full factorization of G. So here we have two distinct roots with multiplicities, and our Galois group is isomorphic to a Z mod 2. An important corollary to the theorem, we have G irreducible over F with degree n. Splitting field K is a separable extension of F. Then n divides the number of elements in the Galois group. To see this, by the theorem, the action's transitive, we can apply the orbit counting formula. So that says the number of elements in an orbit is equal to the order of the group divided by the order of the stabilizer of any element in the orbit. Now, the number of elements in the orbit is equal to n, the number of roots. So that shows that n divides the order of the group, which is what we wanted to show. For examples, we have G an irreducible quadratic over F, K is separable over F, then the order of the Galois group is precisely 2. We know it has an upper bound of 2 factorial, or 2. By the corollary, 2 divides the order of the Galois group, so precisely 2. For concrete examples, okay, first over the rationals we have the quadratic formula. Then the non-trivial element of the Galois group is just given by the sign change in the formula. If we have complex numbers over the reals, there, the non-trivial element of the Galois group is just complex conjugation. Another useful application of the corollary, it will give us the existence of elements in the Galois group, although we may not be able to find them precisely. For instance, if we take a familiar example, okay, the polynomial x to the 5th minus x plus 1 over the rationals. Okay, first note, this polynomial is irreducible over the rationals. By the rational roots test, okay, the only possible rational roots are plus or minus 1, and they're not roots. So if this were reducible, there are no linear factors. So the only possibility is it factors as an irreducible quadratic and irreducible cubic. We also have by Gauss's lemma that this must factor over the integers. So if we put 1 and 2 together, brute force will show there are no solutions of this type. So it has to be irreducible over the rationals. Now that says, by the corollary, the Galois group has order divisible by 5, and then Cauchy's theorem says there must exist an element of order 5, because 5 is prime. So that says the splitting field has an automorphism of order 5. Now, one last group theoretic note. We're not going to come back to this, but definitely worth noting. If I have element of the Galois group, okay, say phi, then this is going to be a linear transformation from K to itself over F, okay, because these automorphisms fix F. Okay, so the automorphism property translates into this condition here, and that just says linear over F. The way I can think of that, we have a one-to-one homomorphism from the Galois group into the group of invertible linear transformations of K over F. This is what we call a group representation. So when we're studying Galois theory, we also have available all the methods of representation theory.